Hey everyone, welcome to another deep dive. This time we're looking into artificial intelligence
Mm.
and its history,
Mm.
which is a lot longer and more surprising than people might think.
Oh, yeah, definitely.
We've got some really cool research and articles you've all sent in, and I'm so excited to see what we find out together.
Well, you might be surprised to learn that even before computers, people have been fascinated with the idea of artificial beings.
Really?
Yeah, we're going to go all the way back to ancient myths and even touch on some early computer science.
Okay, so we're talking way before computers. I'm already intrigued.
We're going to start with Talos. Does that name ring a bell?
Kalos, was that the giant bronze guy?
Exactly. He was a giant bronze automaton guarding the island of Crete.
Okay, yeah. From Greek myths, right?
Right.
I remember that now, but what does a bronze giant have to do with AI?
It's about this basic human desire to create something in our own image, especially intelligence. So Talos and other figures from different cultures, they show that early drive to make something that can think and act on its own. And that drive, that's what ultimately led to the development of AI.
That's a really interesting connection between these mythical beings and what we're trying to do with AI today.
Yeah.
But how did we go from stories and myths to actually trying to make a thinking machine?
That's where math and philosophy come in.
Math and philosophy.
Yeah, thinkers like Aristotle and Euclid, with their work on logic and reasoning, they created a framework for thinking systematically.
Okay.
And that way of thinking, it became crucial for computers and programming.
Wow, so the logic behind computer programs was being developed centuries ago. That's wild. But there still weren't any computers. When did the idea of a thinking machine actually seem possible?
That happened in the mid-20th century. We had new discoveries about the brain, and at the same time, Alan Turing was making huge breakthroughs in computation.
Oh yeah, Alan Turing the codebreaker?
Exactly, and he's considered one of the founding fathers of AI. One of his biggest contributions was the Turing test, which is still important today. Basically, it says that if a machine can have a conversation just like a human, then we can say it's thinking.
So it's about how well a machine can talk like a human. That's a really cool benchmark. But how did we go from this theoretical idea to actually trying to build one?
Around the same time, you had pioneers like Walter Pitts and Warren McCulloch exploring artificial neural networks.
Okay.
And they showed how networks of these simplified artificial neurons could do basic logic functions, kind of like the neurons in our brains.
So they were trying to model the structure of the brain electronically. Were they the first to do that?
They were some of the first, and their work led to some amazing advancements. In fact, one of their students, Marvin Minsky, built the very first neural network machine called the Cesark.
Wow, so this is where we're starting to see the foundation for AI as we know it.
Yeah.
It sounds like things were moving pretty fast at this point. What else was going on in those early years?
It was a really exciting time. We also saw the first cybernetic robots appear.
Robots already.
Yeah, these early robots like W. Gray Walter's tortoises, they were really complex for their time. They used analog circuits to move around instead of digital computers.
So they weren't programmed like robots are today.
Right, they had a different control system.
Yeah.
Think of them as the ancestors of today's robots.
It's amazing how many different ways people were exploring thinking machines back then, from abstract logic to robots and artificial neurons.
Mhm.
It seems like they were tackling this from every angle. Where did things go from there?
Yeah, it was a time of real excitement and optimism. Researchers were making breakthroughs all over the place.
So the field was really taking off.
Mm.
What were some of the biggest things they were able to do?
Well, researchers started developing programs that could solve algebra problems and prove geometric theorems. They could even learn to speak English.
Wow.
Yeah, it was huge. And people really started to believe that human-level intelligence in machines was just around the corner.
I can see why people were so optimistic. Were there any specific programs that really stood out?
Oh, yeah, there were a few that were really impressive, like Daniel Bobraw's program called Student.
Student?
Yeah, it could solve algebra word problems, which showed just how much potential AI had for understanding language, like how we speak.
Mm-hmm.
And then there was Herbert Gellenter's geometry theorem prover, which could, as you might guess, prove these complex geometric theorems.
So they're really making some big leaps.
Yeah, they were.
Did all this progress lead to more attention and funding for AI?
Absolutely. Government agencies, especially DARPA, they put a lot of money into AI research, which led to these big AI labs at universities like MIT, Stanford, and Carnegie Mellon. It was a boom time for the field.
Yeah. So it seemed like AI was on the right track to achieving its goals. But I know there were some challenges later on. What happened?
Yeah, well, even with all that progress, researchers started running into some fundamental limitations. One of the biggest was just the lack of computing power back then. Computers just didn't have enough memory or processing speed to handle the really complex stuff needed for true intelligence.
So the technology wasn't quite there yet to match their ambitions.
Exactly.
Right.
It was like trying to run some super advanced software on an old, slow computer.
Yeah, I get it. Besides the hardware, were there other problems they faced?
Yeah, researchers found that some AI problems were just really tough to crack because of something called the combinatorial explosion.
Combinatorial explosion, that sounds intense.
It basically means that the number of possible solutions to a problem can get insanely huge. So even with really clever algorithms, it's almost impossible to find the best solution.
So even with faster computers, the sheer number of possibilities could still be too much.
Yeah, pretty much. And then you had Moravec's paradox, which added another layer of complexity.
Okay, what's that?
Well, it pointed out that AI could do things humans find hard really easily, like playing chess or proving theorems, but struggled with things we find simple, like recognizing faces or moving around a room.
That is kind of strange. Why would AI be so good at the hard stuff and bad at the easy stuff?
Well, the main approach back then was symbolic reasoning, and it wasn't very good at things that need perception, intuition, and common sense, the stuff humans do naturally.
So things we take for granted were hard to teach computers.
Exactly. All these roadblocks led to less funding and more doubts about whether AI could really do what it promised. This became known as the first AI winter.
So the excitement started to fade as people realized the limitations. What happened to AI research during this AI winter?
Some research continued, but it was definitely a harder time for the field. But even then, some researchers were exploring new ideas that would later become really important. One of the biggest things was the rise of expert systems.
Expert systems. I've heard that term, but I'm not really sure what it means.
So expert systems were basically programs designed to be experts in specific areas, like medical diagnosis or chemical analysis.
Okay.
They used rules and logic taken from human experts to answer questions and solve problems in those specific areas.
So instead of trying to create a general intelligence, they focus on making AI really good at one thing.
Right. And that was a much more realistic goal at the time. They could avoid the problems of common sense reasoning and actually be useful in specific areas.
So they found a way to make AI practical by narrowing its focus. Interesting. But I know that eventually AI came back into the spotlight. What happened?
Well, the success of expert systems was a big part of it. They showed that AI could be useful in the real world, which led to more interest and investment, especially from businesses.
Ah, so AI started to prove its worth.
Exactly. Companies saw that expert systems could make things more efficient and help with decision making. And this wasn't just limited to businesses. Governments also got back into it, partly because of Japan's fifth-generation computer project in the 1980s.
What was that all about?
It was this huge project in Japan. They wanted to make computers that could talk, translate languages, and think like humans. It kicked off a global race to develop advanced AI, which meant more government funding in other countries, too.
So AI was back in the game.
Yeah.
But I'm guessing there were still some debates about the best way forward.
Oh, definitely. Even with all the excitement, there was this growing split between the people who liked the old symbolic reasoning approach and those who were into newer things like neural networks and robotics. This debate went on for years and really shaped the future of AI research.
It sounds like the stage was set for some really interesting new developments.
Yeah.
What happened next in this evolution of AI?
Yeah.
So we've got this tension between the old school symbolic AI
Yeah.
and these newer approaches. What did those alternatives look like?
One of the most exciting things was the return of neural networks. Remember those early attempts to model the brain with electronics? Well, they started making a real comeback in the 1980s. A physicist named John Hopfield, he made this breakthrough by showing how a type of neural network now called a Hopfield net could learn and process information in this really precise mathematical way.
So neural networks were back in the game. Why was that?
Well, it was a few things. Hopfield's work gave it a solid foundation, and then you had researchers like Geoffrey Hinton and David Rumelhart. They made some big progress in developing techniques to train multi-layered neural networks.
Okay.
One of their key contributions was this technique called backpropagation. It totally changed how these networks could learn from data.
Backpropagation, huh? That sounds pretty technical. What was so special about it?
It gave them a much more efficient way to adjust the connections between those artificial neurons in the network so they could learn way more complex patterns from these huge data sets. It was a total game changer for neural networks, and it really set the stage for the deep learning revolution that came later.
So neural networks were making a comeback. What about those other alternative approaches you mentioned, like robotics? Where did they fit in?
Robotics was also changing a lot. Researchers like Rodney Brooks, they started pushing this idea of embodied intelligence. This means that to be truly intelligent, a machine needs a physical body to interact with the world.
So it's not enough to just think abstractly. You have to experience the world.
That's the idea. Brooks and others argued that intelligence comes from the interaction between a brain, a body, and the environment. It challenged that old view that intelligence was just about symbols and abstract concepts.
That's a really interesting way to think about it. How did this embodied intelligence idea change how robots were designed?
Well, they moved away from robots that were programmed with specific rules and behaviors. Instead, they started building robots that could learn and adapt by interacting with the world. These robots were designed to be more flexible and responsive, more like living things.
Makes sense. So it sounds like the field was getting more diverse with all these different approaches competing and working together. Were there other developments that shook things up?
Yeah, in the 1980s, you also had the rise of what's called soft computing. This was a bunch of methods that could deal with uncertainty and imprecision, which traditional AI was really bad at.
So instead of needing everything to be perfectly certain, these methods embraced the messiness of the real world.
Exactly. Techniques like fuzzy logic and probabilistic reasoning and evolutionary computation let AI systems handle situations where information was incomplete or unclear. They accepted that real-world problems often have shades of gray, which was different from that rigid logic-based approach of traditional AI.
This all sounds like really good progress,
Right.
but I know that AI had another winter period. What happened to cause that?
Well, even with all the progress and new interest, all the hype, especially around expert systems, ended up leading to another wave of disappointment.
Oh, no?
Yeah, a lot of those expert systems turned out to be too fragile and too expensive to keep up, and they often didn't live up to what people had hoped for.
So that same pattern of overpromising and underdelivering.
Yeah, unfortunately. That, combined with less government funding and a collapse in the market for specialized AI hardware, led to that second AI winter in the late 80s and early 90s.
But even during this winter, I read that AI was quietly becoming part of our daily lives. Is that true?
It is. While research might have been out of the public eye, AI was being used in all sorts of things behind the scenes. They were powering search engines, improving logistics, and automation making speech recognition better, all kinds of stuff.
So AI was becoming more practical and less about those big dreams of human-level intelligence.
Exactly. This shift to more focused, task-oriented AI worked a lot better and paved the way for the comeback of the field in the late 20th and early 21st centuries. It also let AI become a key part of our technology without anyone really noticing.
And that brings us to deep learning and that renewed quest for artificial general intelligence.
Yeah.
What can you tell us about this new era of AI?
So in the 2000s, deep learning emerged as this huge game changer. Those multi-layered neural networks we talked about earlier. Yeah. Well, with tons of data and much more powerful computers, deep learning algorithms could finally make breakthroughs in things like image recognition, natural language processing, and game playing.
So better algorithms and better hardware really unlock the potential of deep learning. How did this change the field?
It led to this massive surge in investment and interest in AI companies like Google, Microsoft,